Hello and welcome to the YouTube channel D Creations Resources. Today we are going to talk about the Franck Hertz experiment. Now this is a landmark physics experiment and it provided the first direct or experimental evidence for the quantization of energy within atoms. And the Bohr model of the atom was proposed, and this came after that, and it was performed by two scientists, James Franck and Gustav Hertz, in 1914. So they also won a Nobel Prize for it in 1925. And as I said earlier, the experiment demonstrated that atoms can only absorb energy in discrete amounts. And these discrete amounts corresponded to the difference between their allowed energy levels. So this rules out the classical view that the energy is continuous. So what is the apparatus used? It consists of a sealed glass tube filled with a low pressure gas. Originally mercury vapor was used, but now even argon can be used. And inside the tube you have a filament cathode, and when the filament is heated it emits electrons via thermionic emission. Then there is accelerating grid, which is a wire mesh screen which is held at positive potential relative to the cathode, and this grid accelerates the emitted electrons and gives them kinetic energy. There's an anode or collector plate, and that is the metal plate held at a small negative potential relative to the grid, and this small retarding voltage ensures that only electrons with sufficient kinetic energy can reach it. And of course you need to measure the current, voltage, etc. So the accelerating voltage is increased gradually and the resulting current at the anode is measured. So if it was a classical case, according to the classical prediction, one would expect that the current will go on increasing smoothly with the voltage. As the voltage increases, the electrons would move faster and more of them will reach the anode and result in a steadily rising current. But that was not observed. What was observed was the graph of current versus voltage was not smooth. In fact, it showed a series of distinct peaks and troughs. So as the voltage is increased from 0, the current increases, that's fine, but then at a critical voltage. Now if you are thinking historically, then in that experiment at a voltage of 4.9 volt, because mercury was used, the current suddenly and dramatically drops. And after the drop, the current begins to rise again, only to fall at approximately 9.8 volts, which is just twice of 4.9 volts. The next predicted value will of course be 3 times of 4.9 volt, which is 14.7 volt. So the peaks are roughly periodic and they are spaced about 4.9 volts apart. So when the voltage is less than 4.9 volt, the electrons are accelerated, but they don't have enough kinetic energy to disturb the mercury atom's internal structure. They have only elastic collisions. That means the collisions where kinetic energy is conserved, like two billiard balls which are hitting each other. The electron bounces off the mercury atom without losing significant energy. So here the electrons have enough energy to overcome the small retarding voltage and reach the anode, and so the current is rising. Then at exactly 4.9 volt, the electrons have precisely 4.9 electron volt of kinetic energy. This is the exact amount of energy required to excite a mercury atom from its ground state, that is lowest energy, to its first stable excited state. When an electron with this energy is going to collide with a mercury atom, it will have an inelastic collision. Now, in an inelastic collision, the kinetic energy is not conserved. The electron transfers some of its kinetic energy to the mercury atom and excites one of its electrons to a higher energy level. So here it is going to transfer its 4.9 electron volt of kinetic energy to the atom, and so it will be left with no kinetic energy. So it is unable to overcome the retarding voltage, and hence the current is going to decrease. Now again, what happens between 4.9 volt to 9.8 volt? The electron can now have an inelastic collision. It will lose 4.9 electron volt and still have enough leftover kinetic energy to reach the anode. So the current is rising again. Again, when you reach the value of 9.8 volt, which is exactly twice of 4.9 volt, an electron has enough energy to have two inelastic collisions, exciting two different mercury atoms. So after losing 9.8 electron volt, it is left with no kinetic energy again, and it cannot reach the anode, so the current is going to drop again. So this will go on happening, and the values 4.9, 9.8, 14.7, all multiples of 4.9 volt are the values. Now I can give you an analogy to understand this. So imagine a ball, and imagine that you are trying to throw a ball up a staircase. Now if you are thinking classically, it would mean that you can throw the ball with any amount of energy and it will land at a continuous range of heights on the ramp next to the stairs. But if you are thinking the quantum picture, that which is the truth here as per the Franck Hertz experiment, the ball can only land on a specific step. So to get to the first step, you need to give it exactly the right amount of energy, which if it's now mercury atoms, it's 4.9 eV. If you give it less, it just bounces back like elastic collision. If you give it exactly 9.8 electron volt, it can hit the first step. Now the drops in the current are the moments when the ball uses up all its energy to perfectly land on a step and then has no further kinetic energy left. Now if argon is used instead of mercury, the mechanism will be same, but the values of energy are going to be different. So for mercury it was 4.9 eV, but for argon it will be 11.5 electron volt. So then those multiples need to be considered. But the idea, the mechanism, and basically the phenomenon of demonstration of quantization of energy using Franck Hertz experiment is going to be identical. Thank you.